Okay, so we have here a rational function, and I can see that I have factors that cancel. So my restrictions are going to be, before I cancel anything, I need to know my restrictions. I have restrictions at -5 and +1. What's happening locally at -5 and +1? So this factor cancels. So at -5, what's happening? We end up with a hole. Okay, so I should maybe start making a chart here, a table of values, just to keep track of some of my points. So at -5, I have a hole. And this is going to be, if I plug -5 into this expression, I'm going to end up with -30 plus 20 plus 3. So I'm just going to -27. And that's going to be -6 squared is +36. So this simplifies into -3/4. So I have -3/4. And so it's going to be some point very close to the x-axis. Okay, so this is a hole. Whoops, I shouldn't draw that in like that. I should draw it in as a hole. So just to keep track of that, that's my hole. Okay, and I'm just going to make sure that I label that so that I don't mistake that for just a regular coordinate. Okay, at +1 though, we're going to end up with a vertical asymptote. Okay, so I'm just going to put that in here. At +1, I have a vertical asymptote. And I'm going to actually sketch that in. Okay, so I've got some key features here. I should really make note of my 0 because that's from the numerator. So at x equals -2, I have a 0. So it looks like at -2, it crosses the x-axis here. Okay, and I should put in a y-intercept while I'm here. So at x equals 0, when I plug in 0, I'm going to get 1 in the denominator, +1 in the denominator, and +3 in the numerator. So I'm going to have a y-intercept there. Now, that just helps me draw some points. So I know that it's probably going to follow the asymptote, go through the 0, go through the hole, and we're going to show that there is a horizontal asymptote here. It's going to come up from underneath. Okay, so before I get too far ahead of myself, we need to start getting some other parts to this. So we want to do endpoint behavior. So we want to see what's happening at infinity. So the limit as x approaches +infinity, we're going to end up, the denominator dominates, so it's going to be equal to 0. And if we go do a limit as it goes to -infinity, again, same thing, the denominator dominates. It's going to be infinity in the denominator, so I'm going to get 0 as well. Now, this is something that we haven't really talked about, but if I use a bit of sign analysis here, as x goes to +infinity, well, the denominator is always positive because it's squared, and the numerator is going to be going to be positive, so it's going to be approaching positive 0 from a positive side. So it's going to come down to that from the positive side. Okay, and this is not something we really need to know because our other coordinates will help us confirm this. But we can also do this for the negative. So as x goes to -infinity, the denominator is always positive because it's squared. The numerator is -infinity, so it's going to be a negative going to 0 from the negative side. So that's what confirms why it's coming up to infinity, up to the horizontal asymptote. Okay, so I'm going to draw my horizontal asymptote, like this. And just a reminder that functions can cross horizontal asymptotes. They cannot cross vertical asymptotes. So you can see here it crosses the horizontal asymptote at -2. Okay, so now I want to find min and max points. I need a derivative. So my first derivative, I've canceled those out. I'm going to differentiate this using quotient rules. So I end up with 6 times x minus 1 squared minus 6x plus 3 times 2 times x minus 1. Okay, so that's my quotient rule. I need to square the denominator. X minus 1 squared squared, so it's power 4. I should cancel some common factors out before I simplify this because it's going to make it much easier if I recognize that common factor of x minus 1 and cancel those out so that I don't have such big terms to deal with. Okay, so that's a very useful key. Otherwise, your work that you end up doing, having to expand this, is going to be fairly significant. So I end up with minus 12x, just keep track of your signs here, minus 3 times 2 is 6. That's going to be over x minus 1 cubed. Okay, further simplifying this, I end up with negative 6x minus 12, and then I can solve for my min or max point. Okay, so at f prime of x equals 0 at x equals negative 2. Okay, so at x equals negative 2, that solves that equation. I can maybe just show that a little bit clearer by factoring that. Okay, so I'm going to then put my slope chart in here. So at negative 2, what do we have here? Okay, so I don't think I have a 0 here at negative 2. I kind of made a mistake up here. So solving that 0, that actually is going to be at negative 1/2. Okay, so that's going to be negative 1/2 is going to be my 0. So it's actually going to be a 0 right there. Okay, my mistake. When I took a look at this factor, I kind of divided that backwards, so I have to be careful about that. So now at negative 2, and I can kind of see that I made a mistake because I can't have a 0. That 0 was not going to be a minimum point, so I knew that that was something inconsistent. Okay, so there I have my 0 slope. I should check my slope on either side of that. So f prime of negative 3, when I plug negative 3 into there, I get negative times negative on top. So that's going to be negative 6, negative, and then I'm going to have negative in the denominator. So that's going to be negative concavity. Okay, sorry, negative slope. So it's going to be going down towards there. That's going to be a minimum. And then I've got my undefined slope at, where was my vertical asymptote? At positive 1. Need to make sure I have that on my chart. Okay, so between negative 2 and positive 1, I should check my slope. So I'm going to check it at 0. When I plug 0 into there, I end up with negative divided by negative. So that's going to be positive slope. Okay, that's what I should expect. It's going to go up to the asymptote. And on the other side, f prime, I'm going to test it at x equals 2. When I plug x equals 2 in, I end up with negative on top and positive on bottom. So that's going to give us negative slope. So it's going to be negative slope all through there. Okay, and it's actually just going to be a negative slope function through there. So I know that from the asymptote, it comes down. Okay, and since this is a feature that if we have a squared denominator, that means that it's going to be pointing up in the same direction on both sides of the asymptote. Otherwise, it would switch direction if it didn't have that multiplicity of 2 in the denominator. Okay, so I need to establish some coordinates here. my minimum point at -2, I should calculate. So I'm just going to make some room on my table here for that. I'm just going to move my hole over. Okay, so at -2, x is -2. Y is going to be, when I plug -2 into here, I get -12 plus 3, so -9 in the numerator, and then -3 squared in the denominator. So that's going to be -9 divided by +9, which is going to give us -1. So our minimum point happens at -2, -1, right there. Okay. I do want to also put my inflection point in here. Based on what I have so far, I know my graph should look like this. It should come down and follow the asymptotes. Okay, it's going to come down through the intercept, okay, through the y-intercept, through the x-intercept, have a minimum, come back up, and follow the asymptote like that. So there's an inflection point somewhere in there as well. So we should find that inflection point. Okay, so finding the second derivative here. So this inflection point is going to be quite complicated. So this would make this problem from kind of a hard problem to a really hard problem if I were to ask you for the inflection point here. Okay, so this is, if we were to stop here, we can have problems that would just give us this and we can stop. And that would be reasonable. It's still fairly involved. But now adding an inflection point is going to make this a significantly harder problem. Okay, so let's differentiate this one more time. So my second derivative, okay, I'm going to keep my -6 on the outside when I differentiate this. So I'm going to end up with 1 times x minus 1 cubed minus x plus 2 times 3x minus 1 squared. Okay, so then dividing this, I'm going to end up with x minus 1 to the power 6. Okay, so if we want to avoid a lot of work, we can simplify the common factors. So I have a common factor of 2, and take that common factor of x minus, so power 2. So x minus 1 squared, I'm going to divide out of this to make this a more simple looking expression. So f double prime is going to be -6. So when I simplify this, I get x minus 1. And then here I'm going to end up with minus 3x minus 6. Okay, so this becomes x minus 1 to the power 4. Okay, I can simplify this. My second derivative is going to be -6, -2x minus 7. Okay, so again, further simplifying this, I've got a bunch of negatives in there that I can combine. So this is going to be +6, 2x plus 7. Okay, so my second derivative is equal to 0 at x equals -3.5. Okay, so I'm going to put that into my chart here. Well, I'm going to have to put that over here. So although it fits in here, -3.5 really kind of goes up there, but -3.5 as my coordinate. Okay, plugging that into my calculator here, I'm going to end up with 6 times -3.5 plus 3. So 6 times -3.5 plus 3, that gives me -18 in the numerator, and then I get -4.5 squared. Okay, so divided by -4.5 squared, and that's going to give me negative 8 over 9. Okay, so just a little bit, uh, almost to negative 1. So I'm just going to make that a little bit nicer here. That looks like a mess. Okay, so this was negative 3.5 or 7 over 2, and negative 8 over 9 is going to be my inflection point. So it's going to be somewhere right about there. Okay, so there's my inflection point. Again, there's that one. We have to be careful with that second derivative because it can get very messy. Although this one, it didn't end up being that messy in the end.